This is Jishan Chowdhury from JC Tuition, and today we're going to be talking about moments. We're already familiar with the fact that forces can make things accelerate, and in this video we're going to look up how forces can also have a turning effect. So here I have a picture of a spanner turning a nut, and I want you to think about how would you maximize the force to turn this nut. Well, I don't know if you have a spanner lying around and maybe you want to try holding it, but I feel like naturally we all tend to grab it towards the end, right at the end, so here, and because we feel like that will give the biggest force, and we'll also twist it and push it at a 90-degree angle. And I think we all naturally do this. In this video, we're going to explore why do we do this and the physics behind it. By the word moment in physics, it's a quantity which tells us about the turning effect of a force. And it depends on two things. It depends on the magnitude of the force and the perpendicular distance of the force from the pivot. Yeah, so the more that makes sense because the more force you put in, the more something's going to turn. And we know that intuitively, if we hold the spanner at its furthest distance, we can turn it more. So therefore, the moment of the force can be defined as the force times the perpendicular distance from the pivot. Now the pivot being the center of the nut from the line of action of the force. So this equation basically sums up everything we've just talked about, moments. So let's imagine we were putting a force on this lever, and here's a pivot in black, and we can call this our force. And let's say we're pushing it at this distance here, and we can call this x1. That's the distance from the pivot. Well, then it's given that moment is equal to force times the perpendicular distance from the pivot. Pretty straightforward. Imagine we weren't pushing it at 90 degrees this way down the lever, and instead decide to push it and put a force in this direction. Yeah, and we'll say it's an angle of theta, and we can call this F2. Well, we know that this will have less of a turning effect because we're not pushing it perpendicularly down. But how we work out the moment in this case? Well, we know that moment is the force times the perpendicular distance of the pivot from the line of action of the force. Well, this is the line of action from the force. So the perpendicular distance from the pivot will be this line here. Yeah, so we can call that x2. So that means for this moment is equal to F2 times x2. How can we work out x2? I mean, we can't just calculate it. With the distance here we can call is d from the end of the spanner. We know that, we can measure that. How can we work out x2? That's very limiting here. Well, hopefully you can see we formed a right angle triangle because the distance, the perpendicular distance from the pivot to the line of action of the force has to be 90 degrees. That's what perpendicular means. So we can use our trigonometry. So we can say that sine of the angle, and we want something that relates our directly measurable things. So we know that we can measure the distance. So sine we know is opposite. So from SOHCAHTOA, we know that sine equals the opposite side divided by the hypotenuse. So the opposite side is x2, and the hypotenuse is distance, which we can directly measure. And therefore, to work out x2, we can just multiply both sides by d. So we get d sine theta. And because that's the equation of x2, we can go ahead and replace that with the x2 here. And therefore, we can work out for this specific scenario that moment equals f2 multiplied by d sine theta. And that's how you go about working out something that's a bit different to just pushing a lever down at 90 degrees. Well, and what this states is that for any object that is in equilibrium, the sum of the clockwise moments about any point provided by the forces acting on the object equals the sum of the anti-clockwise moments about that same point. And that's basically just saying that things are balanced as long as the sum of the clockwise movements is equal to the sum of the anti-clockwise moments. So that's a summary of that. Let's see if I can show this visually using the same lever example. Well, let's imagine we have a force acting downwards here of 4 newtons, and we are 2 meters away from the distance of the pivot. We're going to keep it at 90 degrees. And there's another force acting up here at 2 newtons, and this is 4 meters away from the pivot. Well, the sum of the clockwise moments, where we just do the force times the perpendicular distance from the line of the force, is 2 times 4. So that's 8 newtons per meter, that is 8 newton meter, which is, by the way, the unit of moments. And the sum of the anti-clockwise movements is Well, we've got 2 newtons acting upwards, that's the force, and the perpendicular distance this time is 4, so that is also 8 Newton meters. So this lever will be in equilibrium, it is balanced, it's not moving down or upwards, and that's what the principle of moments is. A real life example to sort of look at the principles of motion as an application to a real problem. So this image is showing an arm, and a human arm basically acts as a pivot. You know, we've got an elbow joint, which acts like a hinge. You know, we can flex and extend, and we've got the bicep muscle, which can help us provide upward force. You know, if you squeeze your bicep, you can basically move the lever upwards. In this question, we've got an object weighing 50 newtons. It's held up in the hand with the forearm at right angles to the upper arm. Using the principles of moments to determine the muscular force F provided by the bicep, given the following data, we've got that the weight of the forearm is 15 newtons, the distance of the bicep from the elbow is 4 centimeters, the distance of center of gravity of the forearm from the elbow is 16 centimeters, and the distance of the object in the hand from the elbow is 35 newtons. So we need to just work out the force provided by the bicep. And we're told that we're using the principle of moments, so we know that the force is balanced. So that means the sum of clockwise movements is going to be equal to the sum of the anti-clockwise movements. Let's go ahead and fill in some of the data. So we've got an object of the weight of 50 newtons, this apple looking object, or maybe it's just a ball. We're told the weight of the forearm is 15 newtons. So the weight of the forearm is giving us a 15 newton weight itself. Distance of the bicep from the elbow is actually filled in for us, so that's 4 centimeters. The distance of the center of gravity of the forearm from the elbow, center of gravity is about there from the elbow, and we're told that's 16 centimeters. And the distance from the hand from the elbow is 35 centimeters. Well, let's remember that force is a vector quantity, so if it's 50 newtons, it should have a much larger magnitude. And the distance here, 35 centimeters. There's a lot of information in this question, so I always like to draw a simplified diagram of what's basically given here. So let's say this is the pivot, our elbow, and here is our arm. So that's our arm. I'll say that's P for pivot, or the elbow. Also, this question, we know the biceps going to be acting as giving a force upwards to contract. So we know the biceps given a force here of F, and the distance from the bicep to the elbow, we're told, is 4 centimeters. 4 centimeters here. What else have we got? We've got the weight of the forearm given 15 newtons, and the distance is 16 centimeters here. And finally, we got the apple ball thing given a weight of 50 newtons at a distance of 35 centimeters. And we know that we're using the principle of moment, and that the arm is balanced at this isometric point. So we can determine the total moments of the clockwise motions, and then determine the motions of the anti-clockwise motions, and then set them equal to each other, because we know that we're in equilibrium. That's what the principle of moments is. So let's do the clockwise moments. Well, clockwise, we've got the weight of the ball at a perpendicular distance of 35 centimeters, so we've got 50 newtons. So we've got the weight of and we've got that the perpendicular distance is 35 centimeters. Remember, the units for moments is Newton per meter, so we want to convert that to meters. So just divide by 100, so that's 0.35. And also in the clockwise direction, we've got the weight of the forearm, which is 15 newtons. So that's providing a force down in the clockwise direction as well. So we can add that as well. So that's 15 times its perpendicular distance from the pivot, which is 16 centimeters, or 0.16 meters. And that means the sum of clockwise moments in the clockwise forces is 19.9 Newton meter. And now we just do the same for the anti-clockwise moments. Well, the only one here is the bicep putting a force upwards. So that is, our force, which is just F, a force which is just F times its perpendicular distance from the pivot, which is 4 centimeters. So that's 0.04 meters. So that's 0.04F simplified. And now we can set these equal to each other, because we know that we're using the principle of moments and they're in equilibrium. So that means 19.9 is equal to 0.04F. And then we can divide both sides by 0.04. That means F is 19.9 divided by 0.04, and therefore F equals 497.5 newtons. So it's just the force, so it's in newtons, which is approximately 500 newtons. And that is the force the bicep is providing. In this question, I imagine there are other forces such as the weight of the triceps also acting to extend the elbow, but in this question we're just given the forces provided in the details in the data, so we can ignore it and just take the other moments around the elbow. So I hope moments and the turning effect of forces makes sense to you now, and please do check out our website and YouTube channel for further videos and tutorials.